Okay. So this first one is the one from the notes the other day that I was like, I'm probably just going to type it up so you don't have to write the whole thing. So, anyways, okay. So is there home field advantage in baseball? In 2007, the home team won 54.26% of 2,431 games. Is this due to natural sampling variability, or is it evidence that there really is home field advantage? So, for our hypothesis, we are going to assume there is no advantage. And P is going to be the proportion of games won. So we're going to have a null hypothesis and then our alternative hypothesis. So our H sub 0 is going to be that P is equal to 0.5. Okay, so that basically the success failure is exactly 50%. So they win 50% of home games. It's just a colon. It just ran together. Well, I initially wrote equal signs, but I was like, well, it's not really supposed to be equal signs. So then I kind of just made them into really big dots. Yeah, it does kind of look like that. And then our alternative hypothesis, it's a little a, just, you know, it's there. And we want that there is home field advantage, so basically that would mean that it's a greater than problem. So greater than 0.5. And so, like I said, this indicates that the home team wins more often. So then for our model, we're going to check the conditions. And it's like, I think I kind of said this the other day, but there's going to be sometimes where we don't really actually do the checking the conditions part like on paper, but you should kind of think through if it fits the criteria beforehand. So independence, we want to know if it's independent. So in this case, we could say roughly that it would be, so roughly true. One season is similar to another. So you've got like team to team, but you've also got, you know, the 2019 season compared to the 2020 season. Now, obviously, that's kind of a completely different scenario because we're looking at a COVID season then. But your 2018 and your 2019 season, overall, it should be about the same. So we can say they'd be independent. Randomization. Technically speaking, for this one, we're not randomly selected, but if I can write here, selected. Okay. But the game should be reasonably represented. Okay, pretty much, I think they play, what, a 162-game season or something like that? I don't know, something like that. I can't remember if it's that or if it's an odd number. But it's approximately even for how many home versus how many away games they play. Baseball. Like MLB baseball. I do too. It's too long. But anyways, so there should be, I mean, overall, I'm pretty sure they all play every team. But obviously in their division, they play some teams more than once. But you can say it's random enough because every team has that aspect of playing, you know. No. Our 10% condition, this will be less than 10%. of all games ever played. And success, failure, we really shouldn't have to worry about this a whole lot, but our NP and our NQ, 2431 times 0.5, 2431 times 0.5, and these are both 1215.5, and both of those are greater than 10, so we satisfy that condition. So we can say we technically satisfy all 4 conditions. I kind of wrote that one a little high up. Whoop. Alright, so then the mechanics. So this is more like the actual math part. So like I said, typically we'll skip the actual writing down the stuff for the model itself. Let's see, where did I? So this technically meets the conditions for a normal model and a one-prop z-test. So then as far as our mechanics, our mu, or our mean, is p sub 0, which is going to be 0.5. It's from the null. Okay, so from the null hypothesis that we had up here. Our standard deviation of p hat is the square root of the initial p, the initial q over n. It's going to be the square root of 0.5 times 0.5 over 2,431. And that value comes out to be 0.01014. Let's see. I think we should be able to do this one on our calculator now, since we said it meets the requirements for the one prop z test. Which should be number 5 on your calculator. Let's see. So I'm trying to check and make sure this is going to work first. I'm just trying to check and make sure this is going to work before we do this. Okay, so yeah, this is going to work. Okay, so on your calculator, you're going to go to stat and then over to test and number 5, which is the one prop z test. And it's going to ask you for your P0, which is 0.5, your X. So our X value is the 54.26% of the 2,413. So Well, technically 0.5426 times 2,431 is what's going to give you that number, and it ends up being 1,319. And then our n value is 2,431. And then it asks you lastly to write which scenario we're using. So ours is the right tail, so it's greater than our P0. And then you just hit calculate. And so then we can get our Z value. So our Z is 4.2. And they go on and do stuff with the Z table, but I'm not sure that we actually need to do that. But the probability of Z being greater than or equal to 4.2 is less than 0.001. But I don't think that our problems actually require us to do that part when we get to the... Oh, wait. Sorry. No, that's not the right number. Okay. Anyways, yeah, you can ignore that. So just for if we were to look at our curve, we've got 0.5 here, and then over here on this side is our 0.54. So we're looking at the right-tailed part of this. Okay, so for the conclusion, I don't expect your conclusion to be this elaborate. Typically, your conclusion for me will look something like, I reject or I fail to reject the null hypothesis, and then it'll say, so there is enough evidence or there's not enough evidence to reject. So there in the notes was a little bit more elaborate, so I'll do the elaborate one here, and then we'll just do the short one when we do the other examples. So a p-value of less than 0.001 says that if there was no home field advantage and the true proportion of home wins was P is equal to 0.5, then an observed value of 0.5426 or larger would occur less than 1 out of 1,000 times. A p-value that small would cause me to reject the null hypothesis and shows that there appears to be enough evidence of home field advantage Okay, so basically, I'll see if I can underline it here in green. Basically, just this last, I don't know if you can see this, but just this last sentence here is all that, it's kind of hard with the lighting, but it's all that I would require you to write as far as your conclusion. And then they do go on. It doesn't ask us for this in the problem, but if we created a 95% confidence interval with this data, we get 0.52277 to 0.56238 for the true P of home team wins. Whoa. Oh, too much. I was trying to fix the light so you could see the line that's underneath the last sentence. It's just like a lime green, so it's like doesn't show up super great on like the board. Because I have the dark green one at home for grading papers. So, this is just the other little piece of notes that they just like had written, but I don't really think, I'm not really going to have you guys do this, so I'm not going to have you write it down. But basically it just says that your conclusion of any test should include the p-value. Let the reader decide if they agree with your conclusion and follow your test with a confidence interval. So typically the problem is going to ask for your p-value when you're finding this stuff, and then it's going to ask, well, it might ask for your confidence interval. I'm not sure how this book does it. I haven't looked that closely at the homework problems yet. And then they just talk about if you use a normal table to pay attention to the different values, which we haven't really seen that yet. So I'll have to go find those tables too and make sure you guys have access to those. But that stuff's not super relevant. So there's that. Now I have to find out where I put, no, here they are. All right. Let's see. All right, so for number 2, it just asks you to write the null and alternative hypothesis, and so that's all these ones want you to do. So we'll kind of look at the why behind these ones. So first, we field test a new flavor soft drink, planning to market it only if we are sure that over 60% of people like the flavor. So whatever percentage is given to you, well, 2 things. We always convert it to a decimal for our p-value, or for the p that we're writing as our hypothesis. Okay. And then pretty much always the number that's given to you about that percentage is what we're dealing with. So our null hypothesis for this one is going to be p is equal to 0.60. And then we have to look for keywords when we're deciding if we're doing a right tail, left tail, or two-tailed test. Okay, so the key part here is over 60%. So that means we need the greater than option. So we're going to have a right tail test. So our alternative hypothesis is p is greater than 0.60, meaning it's a right-tailed problem. All right, so for the next one then, 20% of cars of a certain model have needed costly transmission work after being driven between 50,000 and 100,000 miles. The manufacturer hopes that a redesign of a transmission component has solved this problem. Okay, so Well, to start out with, we always know our null is what's given to us. So our h sub 0 is p is equal to 0.20. So this one is a little more confusing the way it's written. Typically, it will have words like less than, greater than, over, or differs or something like that, changes, is going to be your key words. But with this one, it's a little bit more confusing because it doesn't specifically have one of those words in there. But looking at a redesign hopes that he solves this problem. That's kind of going to tell you that he's hoping it gets it down to less than 20%. Okay, because obviously he doesn't want to have more than that. So our alternate hypothesis is going to be p is less than 0.20. So this one is also going to be a one-tail, but it's going to be a left tail test. Okay, and your book might be writing them as just like a one-tailed test, and they might say lower or upper, lower meaning left, upper meaning right, but I typically just say right and left because it's more clear as to what you're looking at. Alright, so then this last one of these. In the 1950s, only about 40% of high school graduates went on to college. Has the percentage changed? Okay, so our keyword here is changed. It doesn't say has it gotten bigger, has it like shrunk. It just says has it changed. So in this case we're going to have a two-tailed test, but our null hypothesis is going to be that p is equal to 0.40. So our alternative hypothesis is p, and we're going to say is not equal to 0.40. So that means it could be on either side of it, but it's just not the 0.40. So this is a two-tailed test. Any questions about how we determine those or anything? Okay. All right, let's look at this one. Okay, so the seller of a loaded die claims that it will favor 6. We don't believe their claim, and we roll the die 200 times to test an appropriate hypothesis. Our p-value turns out to be 0.03, so which conclusion is appropriate, and we want to explain. Okay? So basically, this person is claiming that they have like your typical die and that it's going to favor rolling a 6 every time. So we're still looking at a classic 6-sided dice when we're looking at this. So our null hypothesis is going to be p is equal to 1 out of 6, okay, or whatever that decimal is. 1 divided by 6. 0.17. Okay. Our alternative hypothesis, okay, is we're saying that, let's see, they say that it favors it, so that would mean that it's going to be greater than this, okay, because it's favoring the 6, meaning it happens more frequently than 1 out of 6 times, so it's going to be greater than, so h sub a is p is greater than the 1 out of 6 or the 0.17. So just to kind of help see here. So this top one, the null is basically the probability that it's fair. The bottom one, our alternate, is the die is unfair, or favors the 6. Okay, so looking at our options here, we want to know which of these conclusions is appropriate. So basically, there's a 3% chance that the dice is fair. There's a 97% chance that the dice is fair. There's a 3% chance that the loaded die could randomly produce the results we observed, so it's reasonable to conclude that the die is fair. Or, there's a 3% chance that a fair die could randomly produce the results we observed, so it's reasonable to conclude the die is loaded. So, what do you think? So which option do you think that is then? So a 97% chance that it's fair is what you think. Okay. Let's see. Oh, it tells us what our p-value is. Okay, so we're told that our p-value is 0.03, okay, which means 3% chance. Okay. So, this is, just to kind of explain here, this is the probability of our sample results given that the null hypothesis is true. So that basically is going to take out, okay, our both A and B. We can get rid of those ones. Okay. Now, as far as C and D, okay, essentially this p-value is telling us that there's a 3% chance that we could produce the results that they're talking about, that it's loaded. Okay? So it would be more so here D that we're looking for. So then when our p-value is low, we're going to reject the null hypothesis. So because p of 0.03 is low, it's a really low value, we're going to reject our H sub 0, say our null hypothesis, in favor of our alternate hypothesis. What? Alright, let's see. Do we want to do one more? Let's go ahead and do one more. Get one that's a little more involved here. Alright, someone hands you a box of a dozen chocolate-covered candies, telling you that half are vanilla creams and the other half peanut butter. You pick candies at random and discover the first 3 you eat are all vanilla. If there really were 6 vanilla and 6 peanut butter candies in the box, what is the probability that you would have picked 3 vanillas in a row? So this particular part is kind of review. So how would I do the probability of this? Yeah. Yes. Well, so you'll have to subtract one. So your first one, like you said, your first pick would be a 6 out of 12, which is, yes, is 50%. But then we need to account for the other two that we pull out. Okay, so we've pulled one vanilla at this point, meaning how many vanilla are left? So 5 are left, and we had gotten rid of one on the bottom, so we have to get rid of another, so now there's 11. And then now you've pulled 2 vanillas, so the third one, 4 out of 10. And then you would just multiply this, and assuming I have this correct, it's 0.091. Okay, so this is our p-value now. And it's kind of low, but it's not too low. So, kind of going to jump to part B and then kind of go back to A a little bit. So, do you think there really might have been 6 of each? So, there are what we call alpha levels. And there are different ones, but oh, I wrote that on the wrong one. Oops. Alpha levels. So we have an alpha of 0.1, an alpha of 0.05, and an alpha of 0.01. Those are going to be the most common ones that we're using. And so with this is going to give us essentially the threshold where we decide to reject or not reject the null hypothesis. So with this, what happens is that essentially it'll tell you for an alpha level, I can't remember if it always says alpha level, but sometimes it'll say like a confidence level, but it'll tell you for alpha to be 0.05, do we reject or fail to reject? And then there's a table of values, which when they were taking their online stats class, there was a really nice table. So hopefully our book has one, or I can find one like they had. But it'll have all the confidence levels, and it'll list all the stuff that you need to decide if we are going to reject it or not. Because your p-value is going to be less than our value here at this. And if it's less than, we reject. If it's greater than, we do not reject. So, based on that, so for here, it's possible then that there are 6 vanilla and 6 peanut butter. Okay, but we're not, there's still a possibility. We don't know for sure because it really depends on what confidence level we're going to use. But anyways, so then for the next part, would you continue to believe that half are vanilla if the fourth one you try is all vanilla, or is also vanilla? So that means that we're going to take the probability we found up here, and we're going to look at if the fourth one was a vanilla. So we had 6 out of 12, 5 out of 11, 4 out of 10, and then now 3 out of 9. And now we're at 0.03. Okay, so this p-value is now low. So we will reject the null hypothesis okay? That there are 6 vanilla and 6 peanut butter. So it is possible there are more than 6 vanilla. Okay. Now obviously there are things that could factor into this, like a box of chocolates literally could be that in one row they're all vanilla and then the other row is all peanut butter, and it could be that they're pulling from the same row every time. So there's other factors that could play into it, so it's not saying this is completely foolproof, but in general we would say that most likely it's very possible that there's more than the amount that they said based on what our data gave us if we kept pulling vanilla ones in this case. Let's see. I think that's probably good for today. We can pick up the rest of these tomorrow and call it a day.